Hey guys, hope everybody's doing okay. What we're going to do today is look at a quick lesson that involves equilibrium and gases. All right, pretty quick lesson today, just some small details that we have to worry about when we have gases in our equilibrium system. There'll be a short equation that we use as well, and we'll just go through a couple quick practice problems. So the example problem I'll start with says some NH3 is placed in an evacuated flask. So we have an empty flask. We're adding some NH3 to that, all right? There's nothing else in there, so what does that tell us? That tells us the equilibrium will shift to the reactant side, right? Because initially we had no reactants at all, okay? Initially we had none of those. Since we initially had none of those, of course the equilibrium system will shift in that direction, right? So some of the NH3 will decompose into 3 moles of hydrogen and 1 mole of nitrogen gas. Okay, it gives us a couple partial pressures here when we're at equilibrium. All right, we're in a 250 milliliter flask. It says what's the Kp value? So Kp is really no different than Kc or Keq, which is really the same thing. We'll learn about something called Ksp and learn about something called Kq a little later on. So you find it the same way. So here's our Kp expression. It's products divided by reactants. Same rules apply. Some difference you'll notice though is that we have this capital P written here a couple times. That stands for partial pressure, or the pressure of, okay? So the pressure of NH3, pressure of N2, pressure of H2. A small little detail here, and notice how we have Kp because we're dealing with the pressures. The units are in pressure, okay? Additionally, another difference, parentheses instead of brackets, okay? So please be careful when you write these. Brackets are with concentration, Kc or Keq or Kq later on down the road, Ksp then later on down the road. Parentheses only for Kp with gases, with your pressures. Okay? It's important that Kp is not equal to Keq or Kc, because Kp is when you deal with pressure. Keq is when you deal with concentration. Okay? I can find the concentration of these gases. Remember, concentration is moles per liter, right? I could find the moles. I know how many liters from the size of my flask. I could figure out what these concentrations are and determine a Keq value. That's going to be a different numerical value from the Kp value because we're using pressures for Kp. All right, so keep that in mind. There are two different values. They're just found the same way, but the numbers differ because the units differ. So you can see through my writing here, the same thing I just said. It's calculated the same, but it's not equal. They're not equal to one another. So the example I think you have in your notes is this generic equation. We looked at this same equation, I think, when I introduced equilibrium. A plus B yields C plus D. So here's your overall format for your Kp expression. You take a minute, jot it down if you need to on your note sheet. So again, it's calculated the same way, it is not equal. Okay, great example here. You have some nickel compound, right? Breaks down into Ni plus CO, right? States of matter here, gas, solid, gas. Two ways to write this. Kc or Keq is when you have your concentrations. Notice the brackets that are here. Kp is with parentheses and the P for pressure. All right. And notice that nickel, not in either of these. Same rules apply. It's a solid. All right. Solids are never included in a Kp, Ksp, Keq, Kc, Kq, whatever. They're never included, right? Because you don't have solids or liquids included in an equilibrium expression. All right. So these are your two options here. It all depends on what I'm asking for. Am I asking for the Kc or the Kp? Small little detail. What I can do is, once I know one of these, I could easily convert from one to the other. So I'm going to derive this very quickly here. Do not worry about how this is derived. But we have PV equals nRT, right? Ideal gas law. You could rearrange that and get P equals N over V RT, all right? Just reorganizing that. What you can do then is substitute in that expression, like substitute what we just had on the previous slide into the expression for Kp for each substance, okay? So here we have this for pressure, right? Substitute that in to every single pressure in your expression. Simplify, and you get something like this, okay? You get Kp equals Kc times RT to the delta N, all right? So Kp is your equilibrium expression with pressures. Kc is your equilibrium, constant with concentrations. R, gas constant, all right? So we'll look at that on the next slide. Temperature in Kelvin, okay? Delta N is the change in moles right here, okay? So it is the moles of gas minus moles of reactant, okay? And this is so important. It's only moles of gas, all right? We're talking about Kp here, right? P for pressure is created by the gases, all right? This is so easy, but students make silly mistakes all the time because they just count moles of everything. It is moles of gas. Please write that on your note sheet. Okay? So the R value is 0.08206 liter atmosphere per mole Kelvin. Okay? Notice that is in atmospheres. So our pressures, we should have these in our equation, right? Not in millimeters of mercury or torr or pascals or something, but we're using the R value for atmospheres. Temperatures in Kelvin, right? Like usual, we're good to go. A good shortcut for you. If the total number of moles of gas is unchanged, as I should say is, right, is unchanged from reactants to products, look what happens. Kp is Kc RT to the delta N. If the product number of moles and the reactant number of moles is the same, then your delta N is 0, right? Well, what's anything to the 0th power? Well, it's 1. So Kp equals Kc times 1. Kp equals Kc when moles of gas, okay, gas, all right, when moles of gas are the same on the product and the reactant side. Really quick and easy shortcut. I mean, you could do it the long way. Like you could actually do the math, like plug all this in. You're wasting your time because anything to the 0th power is 1, right? So let's try one. Your PCl5 yields PCl3 plus Cl2. Determine Kc if at 250 Celsius the equilibrium pressures of PCl5, PCl3, and Cl2 are 0.875, 0.463, and 1.98 atmospheres. Notice all these are in atmospheres for you already. I want to find the Kc value, all right? So I need to manipulate what I had on the previous slide there. Okay, so let's actually plug all this in and see what we end up with. So your Kp expression will look like this. Pressure of Cl2 times the pressure of PCl3 over pressure of PCl5. Notice how the coefficients here are 1, 1, 1, so I don't have to raise anything to any exponent. All right, so pressure of Cl2, that was 1.98 times the pressure of PCl3, which is 0.463, divided by the pressure of PCl5, which was 0.875. Okay, 1.98 times 0.463 over 0.875 gives you a Kp value of 1.05. Okay, we want to convert that into a Kc value. So we have our equation here, Kp equals Kc RT to the delta N. Let's figure out delta N. Okay, figure it out and then we'll check our answer here. Delta N is going to be moles of gaseous product minus moles of gaseous reactant. Okay, so we have 1 mole PCl3, 1 mole Cl2, 1 mole PCl5. So the moles of gaseous product, 2, minus moles of gaseous reactant, 1, equals 1. Okay, so your delta N is 1. Reorganize my equation. I get Kc equals Kp over RT to the delta N. I'm just using algebra to solve for Kc because that's what I want in this problem. So plug it all in. You get 1.05, which was your Kp value, divided by RT to the delta N. So you have 0.08206 times 523 Kelvin, because I converted the 250 Celsius into Kelvin by adding 273. And it's raised to the first power. Type all in my calculator, I get a Kc value of 0.0245. Okay? So you can see the difference there. We have Kp as 1.05 and Kc as 0.0245. So whatever one I'm asking you for, we could easily get. Okay? So a little bit of work here to figure out what your Kp value was, but not a very difficult setup here. Since all the exponents are 1, so all your coefficients are 1. Okay, it's a couple other practice problems in your packet. We're going to go through those real quick. And then we'll call it a lesson here. So calculate Kc for the following. You have CO plus Cl2 yields CoCl2. I give you the Kp already at 727 Celsius. Okay, take a second, figure it out, and then we'll see if we are correct or not. Okay, same process. Right, we have Kp as Kc RT to the delta N. So write it out. So in this case, we have our Kp value already. We want to solve for Kc. I know what R is. My temperature is 727 plus 273. That gives me 1000 Kelvin. And what else? Delta N. What should the delta N be? I have 1 mole product minus 2 moles of gaseous reactant. So delta N is -1. All right, so that's important there. It could be negative. It's no big deal, right? It just follow the rules. Product minus reactant. 1 mole of product, 2 moles of reactant. 1 minus 2 is -1. Plug all of it in, and we should end up with Kc value of 3.2. Okay? Make sure you do R times T. Okay? Make sure you type that in and like hit equals or put it in parentheses, right? So you have 0.08206 times 1000. That is raised to the negative first power. Okay? And then you're going to end up with your Kp value divided by that. You'll have Kp over RT delta N, which is the negative first. Okay? Don't make silly math mistakes here. That's really the only thing you're going to screw up is a dumb math mistake, because none of this stuff is really all that difficult. Okay? So Kc value 3.2 is what you should end up with. Next one, what's the Keq for the following reaction given that Kp is 49? Okay, take a second, give it a try, and then we'll go over it. Okay, real easy. The answer is 49. No math required, right? If you go back a couple slides, if you were moles of product, which is 2, okay? So moles of product, moles of reactant, gas reactant, 1 and 1 is 2, okay? Moles of reactant, moles of product, if they're the same, your delta N is 0, and your Kp is equal to your Kc. Okay, that's from a couple slides ago. Because you're raising RT to the 0th power. Anything to the 0th power is 1. So you end up with Kp equals Kc, RT, sloppy RT, delta N is 0. Well, that makes that 1. There you go. Kp equals Kc. Save yourself some time and make sure you know that rule. Last one. I want the delta N. Okay. What's the change in moles for the following reaction? What is the delta N? Take a second and we'll go over it. Okay. Do not make a dumb mistake here. It's the moles of gaseous product, which is 1, 2, minus the moles of gaseous reactant. That's the only gas. Carbon's a solid. You don't count it. Delta N's 1. Okay? So, very, very easy question. Hopefully you didn't make that silly mistake. And it's all about a lot of things in this class, which is that attention to detail, right? So, it's really easy to say, oh, 2 minus 2 is 0. We're good to go. Because it is 2 moles of product, 2 moles of reactant. But the detail we're worried about is gaseous product, gaseous reactant, okay? So you want to make sure you're slowing down a little bit when necessary and paying attention to those small little details there, okay? That's really about it, guys. You won't have to do this too often. Pretty straightforward and takes care of it. So short lesson here, and if you have any questions, let me know. Thanks, guys.